Hello, everyone.
Hello.
Let me make sure that everything's in place. How are you doing, guys?
So far, so good.
I'm today not my home, so I'm in the office. I realize my camera is a little bit too high. It's probably will be too large. Sorry, I was end up to be doing experiments for too long, and then I realized, oh my god, it's almost 5 o'clock, and I need to move the lab from here to the office. And I realized that I need to set up everything back. And I think this is a little bit too big. Let me move my camera down, and we'll start in the middle.
Good.
To do that, I just need to make a pile of books and put my stand on pile of books so I will have a proper height. So before I had it on a shelf, and on a shelf it's a little bit too high for you guys. So I just need to find proper amount of physics books which will allow me to have for you a proper height of the piece of paper. Okay. Okay. Let's see. I think that should be fine. Just we need to have a one thick book on top of it, so nothing will fall off. Great. And
Cool.
probably one more big book up. Sorry. I'll show you my assembling, such as you end up to be in a situation of waiting me to get it done. I'll show you my computer. That's my assembling of books with a piece of paper.
It looks so high tech.
Exactly. How many fixes books do I need to make it right for you guys? Okay.
I think the order of chaos could be pretty high there, though.
Yeah. Okay. So I think we set it just. If you hear a big sound, it implies all this pile of books have fell off. Okay, come on. At home, I was spending like an hour of testing it. Today, I just decided to go to the lab, and I thought, oh, you know what? It will be very easy to replicate what I did at home with all these books, but that was wrong. It's not as easy as it may think. Okay, I think somehow it doesn't give me the right angle. Sorry, guys. Just want to make sure that. Guys, tell me one thing while I'm doing this tedious job. Would you like me to post these notes for you, or you're fine with what is going on now?
I wouldn't mind the notes posted. That could help.
Will you continue to write the notes and listen carefully?
Yes.
You all give me the pinky promise.
I will.
Okay.
Yes.
You would like to have it, because I want you to write your notes, because I could tell you from teaching the class, if people taking a good notes themselves, that make a big difference. And pinky promise, okay. Okay. Great. Okay, so I set it up. I think it's pretty good, guys. Let me know if I end up to be out of scale with my piece of paper. I think I'm in a good shape, and I'm okay. Let me put this video.
Is it just me, or is it kind of blurry?
So I'm getting your network bandwidth is low, and so it makes the image blurry and also smaller, at least on my end.
Huh. You're absolutely right. Let me see what's going on. You know what, guys, I'm really sorry. This is what happened. I tested well at my homework at home. At my home, I spent like a week or two thinking how I'll teach you a class from home. But I never thought, oh, I will go to the lectures in the office. It will be so much easier. It will be better internet. It's not. Okay. And I know if I'll switch it for you to the whiteboard, which I have in my office, it will not work. So, okay, guys, it will not work like that. Let's see if it will go on a whiteboard. Will you see well whiteboard if I'll move to whiteboard? Let's try to do whiteboard, okay? So I will unpin this one.
I see that you're using your phone. I see that you're using your phone for the video.
Yeah.
Are you on the Wi-Fi or on the cellular?
I'm on a Wi-Fi. Oh, no, I'm not sure. I'm to be honest, here on the campus, I'm not sure. Okay, guys, I will use a whiteboard this time, okay? Let's see if it will work for you guys. If not, sorry, today will be lectures hectic. I promise next time all my lectures will be at home with defined technical issues. Okay? So we'll have it this way. Let me know if you couldn't see it. And oh, could I make one test, guys? If I write here a word, let's say physics, do you see it properly or you see it mirrored? You could not see it at all. It's too light. Yes.
It's really
faint.
Yeah, it's really faint.
I'm really sorry, guys. We'll spend the next 2 more minutes. I will fight with my phone to put it in a proper band. That was okay. I feel very sorry for you guys. I usually promise I'm much more organized. It's just I spend too much time in the lab and okay. Tell me how are you? Tell me something fun. Or otherwise you'll hear my silly physics jokes.
I wouldn't mind the silly physics jokes.
Okay.
Let's hear them.
Okay. While I'm doing with technical difficulties, I'll tell you. Who knows the joke about spherical cow? I'm going over jokes which every physics students have to know.
Never heard of it.
Really? You're kidding me. How could you call yourself a physicist if you don't know anything about spherical cow? In this case, as your teacher, I must make sure you get a proper education as in physics jokes. So, while I'm doing that, sorry, I'll just connecting to Wi-Fi while I'm doing it. So, people decided to find out how to raise better cows, yeah, and they decided to give monies to biologists, engineers, and physicists, yeah. The biologists find out, okay, if we have this particular genomes, they will produce a high level of milk and will do this modification. This is the most reliable. Engineers, they find out, okay, if we make this new building structures, it will create cows in much better conditions. And in this case, this milk will automatically go to the canisters and so on. And now they ask a physicist, and the physicist said, okay, we get great results. We already find out how spherical cow will behave in vacuum. Okay. So that's what we as a physicists do. We sometimes do spherical cows in a vacuum, which are completely useless models. Because spherical is the most easiest form, and vacuum is, again, we don't need to worry about anything related to the air resistance. So
very ideal, very ideal.
Exactly. So let's me hope that it's connected now, and otherwise I'll have to tell you another joke. So that's the deal. If I'm having troubles, at least I will be able to tell you jokes. Just a second. But spherical cow, it's a classic. I'll need to, in this case, give you a link for all the physics jokes which uploads every week. And as a physics major or astrophysics major, you should, I will not tell you it's your homework, guys, but it will be your free time things to check out there for jokes. Okay, is this, let me see if I will spot this video. Is it better? I think it's better, guys, yeah?
Yeah.
Perfect, great. So, should I tell you a second joke? Or skip it out for next time? Okay, one more joke. Tell me which one I will tell you. Okay, guys came into in psycho center, you know, like where is all the crazy people, and this crazy person coming to one person and say, "I will differentiate you." You're like, "Oh my God, don't differentiate me." Guys come to another person, say, "I will differentiate you." "Oh, please don't differentiate me." Then he comes to the third person, "I will differentiate you." "I don't care." "I will differentiate you twice." "I still don't care." "I will differentiate you like 10 times." "I don't care. I'm exponential." So I'm done with my silly jokes. So now let's move to ideal gas. Okay. So our third topic, just change of subject. Yeah. So last time, guys, what we discussed? Last time we covered with you what? Who remember? We covered with you what is a microscopic point of view, microscopic, yeah? And we discussed with you temperature. Okay, let me also open the chat box so I could see your chat comments. Okay. Thank you. I see it all now. Okay, so today we'll talk number 3. Okay. So we will talk today about ideal gases. Number 3 is ideal gas. Okay. I promise I'll tell you more jokes. I'm hoping you'll be in my lectures for longer than one lecture, so you'll have a lot of physics jokes. Okay, so second under the subsection, first we'll talk about ideal gas laws. The ideal gas law. I'm sorry, before I switch the topics, sorry, one more thing, news. Guys, I upload for you homework. Did you see it?
Yes.
Yes.
Oh, good. So you saw homework. Okay. Sorry. It was yes. Cool. It really doesn't like this office. It really doesn't like me to teach you lectures from the office. They said, go home. Don't never do this again. Okay. So ideal gas law. And so you have a, sorry, you see I'm very unorganized today. So homework is on my website. I make pictures for you for that. You can do the homework. Please make sure you submit. And as you're requesting for me, you'll have these notes, the one which was organized last time, and you will not see the unorganized 15 minutes which we just talked about, but from this point of view, you'll have organized copy of the notes online. Okay, that's why I don't want to have pre-recording. I remember somebody asked, will you put the videos in it and save it? No, because if I'll tell you jokes, I will do this type of things. You will not have a physical evidence. Okay.
You have to add the jokes to the notes.
Yeah, no, that will be only for students who are attending the lectures, and pay attention to that. The only one who deserve it. Okay, let's go back to the lectures. So we'll talk about ideal gas law. So people did quite a lot of experiments in several hundred years ago, in the last 2 centuries. So one of them was Boyle, and he found out very interesting behavior. He found out if we have a constant temperature and constant amount of gas, Okay, now we'll focus, guys. Sorry, I know I make you all not focus on physics, but let's focus now. So we have a constant temperature and constant amount of gas. In this case, we have a relationship that PV is equal constant, and it's constants both Boyle constants, yeah. And this is work for constant temperature and constant amount of gas. Okay, so he find out that. Then, and you should understand it's quite a hard thing. They sort of make a constant temperature, try to control, and then they find out this relationship. As you increase the pressure, the volume change. Then another guy called Charles, he's come up with his law. He find out if we have a constant pressure and constant amount of gas, we don't add extra gas. In this case, volume is equal constant of Charles times temperature. And this is for constant pressure and constant amount of gas. Okay. Okay. Now another guy who is Avogadro, and you know the Avogadro. He find out that there is a relationship between volume and how much moles of gas we have, and he find out that is equal to volume equal constant, Avogadro constant times n, where we have a given temperature and pressure. Okay, so equal volume of a gas contains equal number of moles. So that's for constant temperature and constant pressure. And that's what he found out. He found out that equal volumes of gases contains equal number of moles. Equal number of moles. Which is quite a cool idea. So let's turn it around, guys. So it implies that you have 1 mole of oxygen or 1 mole of nitrogen. It will all take the same amount of volume, and we'll discuss what is this volume is. Who knows how much volume takes 1 mole of gas? Please remember it.
6.022 times 10 to the 23rd.
That's amount of molecules. Very good. It's an Avogadro number. But what is the volume it takes 1 mole?
Is it? But this is at a set temperature and pressure, right?
You put me in a spot. I think it's an irregular
yeah, room temperature.
Here it is moles and volumes. Yes.
Is it 22 liters?
22.4 liters. Yes. 22.4 liters is the amount of volume it takes for 1 mole of gas. You're absolutely right. Okay. So I could write you down that 1 mole occupies equal to 22, not equal, proportional, yeah, to 22.4 liters. Okay. Okay. So this is all laws, and they were all separate. And you should understand it takes a lot of experimental data. We're taking all this for granted, but these people spend years trying to find the relationship for different gases and how they relate to one with each other. Okay. Okay. So and then they managed to come up with one big ideal gas law, which you probably see before, and you're taking it for granted. Ideal gas law, which is equal to PV is equal to nRT. Okay, where P is the pressure and it's measured in pascals, which is equal newtons divided by meter square. Yeah. And what is sometimes we measure pressure in atmospheres, and how it's related to Pascal is one atmospheric pressure, 1 atmosphere is approximately equal to 1 bar, which is equal to 10 in the power 5 of Pascal. Okay. Then V is a volume, and how we measure volume, we can measure it in meters, and or sometimes they put it in liters. So 1 liter is equal to 0.1 meter cubed. So it's 10 in the power minus 3 of meter. Okay. T is a temperature. And here's a very important, this is temperature in kelvins. I could guarantee you at least 1/3 of this class will do at least one mistake in his or her homework or an exam where they confuse kelvins and Celsius. Okay, so it's very important that it's in kelvins. Okay, make sure, try to be not this person who will make this mistake. Okay, but if you will be, just be nice to yourself. You're 1 out of at least 1/3 of the class who will do that. Okay, make sure this temperature in kelvins. So if somebody said that, oh, 20 degrees, remember you'll need to transfer to Kelvin 1. Okay, then N is number of moles. Number of moles of gas. Okay, and R is universal constant, which is equal to 8 times 3.1 joule per mole in Kelvin. Okay, and that's a constant.
It's meter cubed, right, for volume?
Sorry?
Meters cubed?
Oh, sorry, yes. Thank you very much for catching it out. Yes, very good. Yes, I forgot cube there. Okay. So this law, ideal law, was first stated by Clapeyron. He found the relation between PV and T. First stated by Clapeyron in 1834, and he found the relationship not only because here, guys, people find the relationship between P and V, V and T, V and N, only 2 constants, yeah? But he managed to find the relationship between 3 P, V, T, and and find this relationship PV is equal to nRT. And he found out it for ideal gas. And in 1874, Mendeleev generalized it and said that it works for all gases and it will have the same constants R. Mendeleev generalized for all gases. Okay, and it has the same constant. Okay. So, could I move, guys, forward? Yeah.
Yeah.
So 1 mole of gas with 1 mole of gas contains Avogadro number of molecules, yeah? Avogadro's number of molecules. And it is 6.02 times 10 in the power 23. Okay. And we discussed that 1 mole is 22.4 liters. And in this case, if we want to calculate how many molecules we have in a gas, so in this case, we want to find out how many number of molecules. Could I move the first page away? Okay.
Yeah.
Okay, let me zero you out, guys, on your response in case somebody wants to send me a response. I'll see your chat as well. Okay, so number of moles or number of molecules is equal to n, yeah, is equal n number of moles times Na. So number of molecules n is equal number of moles times Avogadro number. And look what we have here. Here we have NR, and what we can rewrite in this case, we can rewrite that NR is equal to NK, where N it will be number of molecules, and we can rewrite ideal gas formula in a different ways. Ideal gas law we can write as PV is equal to NKT. And that's another way how to write the same formula, where K is a Boltzmann's constant. Boltzmann's, double N, Boltzmann's constant. K is equal R over NA, which is equal to 1.381 times 10 in the power minus 23 joules divided by Kelvin. Okay. And why we care about this Boltzmann constants, later you'll see it's quite a universal number. It's quite like R is beautiful when you're talking about moles, but this K we'll see over and over. So you'll see. So let's look at this equation, how powerful it is. So let's look what happened. Let's look at an example. Let's have a situation that we have a gas, a temperature, which is constant. And now we increase the pressure. Pressure increase to 2 pi. So what will happen, to 2p, sorry, pressure increased twice. What will happen with the volume? What will happen with the volume in this case? Will it expand or it will squeeze?
Half.
Okay. Will it expand or it will squeeze? You can turn your speaker and tell me.
It will squeeze.
Yes, it will squeeze and it will be 1/2 of the volume. Okay. Squeeze gas. Okay. Just my way to make sure that you're not fully asleep. At least I have 1 or 2 people who responds back. Sometimes I'll put you in a spot to give me something, answers. You need to remember that this is ideal gas law, is an approximation, and it's never exactly true for real gases, because for real gases, it's work if you have a low density gas, okay? So for other cases, it does not work. Let's maybe write this note for you. So it's ideal gas law is an approximation, okay? It's approximation, and it works for low density gas. Yes, for example, like air, it's not very concentrated, it's quite low density. It's a situation when the size of molecule is less than distance between molecules. Distance between molecules, okay? Significantly less, not just one step. Do you know what this means, double error? Yeah, it implies like significantly, like several orders magnitude. So, for example, at least 10 times or 100 times. In this case, ideal law applies. But not all gases like that, guys. In this case, there is a new modification, and you can modify this formula, and it's called van der Waals equations. So number 2, it will be van der Waals equations. So, and van der Waals equation is pressure plus A is a constant. I'll write for you what constants each of them mean. M square over volume square times V minus NB is equal nRT. Where A, B constant depended on gas or fluids. Depend on gas or fluids. Or fluids. Okay. So you can see if A and B is small, what will happen? If A and B small, these components will go to 0 and this component goes to 0, yeah? And in this case, we'll get our ideal gas, yeah? Formula. But this formula, van der Waals formula, is accurate for all gases and even dense fluids. Works for all gases, even dense gases, and also fluids. Okay. So what this formula takes into account? Let's look on it. So so we can still see this equation. Could you see it, guys? Yeah. Let's just that. Okay. So this law takes in account non-zero volume, takes in account non-zero volume of the particles, okay, and it corresponds to constant P, okay. So you can, and also takes into account interactive interparticle forces, okay, and a pairwise attractive interparticle forces. Attractive interparticles forces. Okay, and this is constant P. Okay.
What's the second word? Low?
Here?
The first.
Oh, this law, sorry, you're right. This
Gotcha.
law takes in account, thank you very much. Sorry, when you write it down, you don't see any mistakes. This law takes in account non-zero volume of a particle, constant B, and a pairwise attractive interparticle forces. Okay. So you can see that here we have volume minus NB, where we're taking into account B is a size to the volume of the particles and N is related to the moles. Yes, so depends how many particles we have there. In this case, from the whole volume which it takes out, we'll remove this volume which particles occupied. And here you have a pressure of the system, but also you have a pressure between each other, you have interaction between each particles, and this is give additional pressure. And here we have this concept of this variable here as well. Okay, clear, guys? Does that make sense? And you'll see this equation again, and I believe I give you a quick homework where you'll need to do it, or maybe not quick, I don't remember which problem, but you should have one problem on it. Van der Waals derived this equation in 1873. Van der Waals derived in 1873 and received Nobel Prize for that in 1910. Okay. So now let's talk about ideal gas, and now we'll all talk about microscopic point of view. We're talking about pressure, volume, temperature. They all macroscopic explanation of the effects. Now let's look at from microscopic point of view of individual particles. So we'll look on microscopic model of an ideal gas. Okay. So let's find a relationship between temperature of a gas and the kinetic energy of the molecule. Okay. So we'll find what is the pressure of a microscopic model of ideal gas. Okay. So let's find a relationship between temperature of gas and the kinetic energy of molecules. And kinetic energy, sorry, I'm cutting out some words. I'm sure you know what this Ke means, yeah? It's kinetic energy. Kinetic energy of the molecules. Okay. I probably start to write bigger. I'm sorry, I start to write smaller. I will keep the large letters. Sorry, I realize I start to squeeze out stuff. Okay, so let's look on the chamber. So let's have a chamber. And here, this is our chamber. And here we have our pistol. Okay. This is our pistol. And the pistol have pistol area, has area A. Okay. And here we have our gas. Here we have our gas, yeah? Right here, gas, okay? Okay. And this is a pistol has a length L, okay? So now, what happened? Theoretically, we have a molecule, yeah, and this molecule will fly around, yeah, bounce back. Each of the molecules will like that, like that, like that, okay? So it will have a different path, yeah? And at each of the point of time, let's say it's moving like this, we can describe it move. Let's see. No. Let me take this point here. So, for example, at any point, this one goes here and it has a velocity v, but we can take on a component of it vx. Okay. So we just look at the molecules. There is multiple molecules. They goes around, they bouncing back and forth. And just let's at this point trace one molecule, because we're trying to go to microscopic point of view. And at some point, it has velocity v as it travels, and there's component vx. What happened with this molecule? Periodically, this molecule will crash on a pistil and bounce off. Yeah. So if it will bounce off, in this case, it will transfer its momentum. Okay. And if it will transfer of momentum, this is a way how we can apply some force on it. And this is what we'll derive. You saw this in your first year of physics, where we're talking about how the pressure and change of momentum related to forces. And this is what we'll discuss with you. I hope you'll hold on me. I know it's a little bit tricky derivation, but try to be with me, okay? I mean, it's not tricky, but it's sort of a little bit long. So let me write it down. So periodically, molecule crashes into pistil. Okay, and bounce off. And bounced off. Okay. So now let's look what will be the average pressure. The average pressure will be equal to this average. It will be Fx average on pistil divided by area. Okay, force divided by area. This is what we know about pressure. But this is force on pistil. But how it's related force on pistil with a force on molecule? It will be same, but sorry, I have some of the paper. Same, but with opposite sign. Yeah. So in this case, it's equal to minus f of x on a molecule. Okay. Okay. Now, force on a molecule is equal to what? It's equal to change of momentum over time. So it will be minus m delta Vx average over delta T divided by area. Okay. How we got it here, guys? Let me explain again. So force on a molecule is equal what? M times AX, and acceleration is equal delta Vx over delta T. Yeah, you can look at it like that. So we can look at this from Newton's second law. Does that make sense, guys? Are you with me? I see some link. I'm glad to hear that. Okay. Okay. Here we have it over delta T, and we're taking about average, so we can choose any time. So delta T can be anything we choose. So let's take delta T time, which takes one molecule undergo the whole circle around, like go back and forth. So in this case, such as could be anything, let's take delta T to undergo one round trip. Okay. In this case, delta T is equal to 2L over Vx. Make sense? Okay. In this case, the change in velocity delta Vx is equal to Vx final minus Vx initial, which is equal to minus Vx minus Vx, which is equal to minus 2Vx. Okay. So in this case, this average pressure, this formula which we have here, we can rewrite, and we can rewrite it that, let me keep it out like this.
Professor, just
Yes.
one moment. So for the change in velocity, I think in the way you define velocity, so it would be minus positive Vx, right? Because if not, it would cancel out.
Yes, you're right. I'm sorry. Here's a plus because it goes in one direction, here plus. Yes. Sorry. In one direction final, it goes in a minus, and so it depends how we define the axis. Sorry. So what we have it, so it goes the whole circle, yes? So in one direction, it goes in one direction, then it will turn around and it will have a minus sign, yes? So sorry, it should be here plus because it's changing. So in one case we go, let's define the axis. So it will make it more sense. So it goes back and bounce back. So let's define our axis here. If this is our axis here. So in one case it will be positive, and in another case it will be negative. Okay. Thank you very much for catching out. But it's equal minus 2Vx. Okay. Thank you. So in this case, we can find that average pressure is equal to minus m over a and minus 2Vx divided by 2L over Vx. Let's see again. So do you see this formula here before? We have minus m over a, delta Vx, it's equal minus 2Vx, and delta t is equal to L over Vx. So I plug them in, and this is what I got. So we can rewrite it, and we can rewrite it as equal mVx squared over AL. And what is AL, guys? What is AL? It's volume, yeah? Volume is equal to A times L, yeah? Volume of the container. We go back to these macroscopic variables like pressure, and here's a volume. So we end up to be having here mVx squared divided by volume. Okay. So let's look at this because that's very interesting. So we have something here where pressure, average pressure, depends on one molecule velocity and the volume. So we have here square, where the square comes from. So we have two Vx's. So one Vx comes from change of velocity, yeah? So the faster movement, more pressure transfers in the collision, yeah? One Vx comes from change of the velocity. So faster the particle moves, more pressure P will result. Okay? So it implies faster movement, more pressure is transferred. In collision. Okay. And we have one more of Vx. Another one Vx comes from delta T. So move faster, more collisions. Yeah. Move faster, more collisions. So now you see why this velocity here makes sense, yeah? Why we have here square, because we have two parameters which cause this pressure. So we have for one molecule, we have that average pressure times the volume is equal to mvx squared. Now, let's see what will happen when we have n molecules. Okay. So now we have n molecules. In this case, we'll go from average pressure to the whole pressure of the system. So that was average pressure for one molecule. Now we're going for the whole system. Okay. So in this case, we have our PV, which is equal to PV of the whole system, is equal to this mv1 x squared for the first molecule plus for the second molecule. V2x, plus so on for more and more molecules. So the total, it will be equal summation up to n of mass times velocity I x squared. Okay, does that make sense? So we have n molecules, so each of them this mv squared transfer to. Now we can say that define that Vx2 with a dash will be average speed of the molecule. For molecule. So for any molecule, the average speed will be like that. Because this one we just said that, oh, we'll teach this molecule and find out what's going on with the second one. But now we're saying that average speed for each of the molecules, Vx squared with a dash. This implies the average, yeah? In this case, we can rewrite this nice formula in a way that PV is equal N mv x squared average. So we have n molecules, and each of them have average velocity. Does it remind you something? We go closer and closer to our ideal gas law. You can see that how we go from microscopic slowly closer and closer. So we know from microscopic point of view, PV is equal NKT. But here we know that PV is equal NMVX squared average of average velocity. So then we can conclude what? We can conclude that KT is equal to mvx squared. Or we can rewrite it as 1/2 mvx squared is equal to 1/2 KT. So 1/2 KT is equal average kinetic energy in x directions. This is average kinetic energy in x direction. We are almost like 1/3 or 2/3 through. But honestly, when I looked at this, every time when I derive it, I feel like it's such a magic almost. Like we're starting from one molecules and we as a physicist, start to do step-by-step logical conclusion, and we derive to completely new concepts. So here we start just one molecule which bounce and transfer the pressure. Now we're finding that what is the relationship between average kinetic energy for any of the molecules. So now let's look at the average kinetic energy. Average kinetic energy, so it's average kinetic energy has in all direction, yes? It could go in x, y, and z. So it should be equal to 1/2 mvx squared average plus 1/2 mvy squared average plus 1/2 mvz squared average. Yeah. So kinetic energy for total is equal to summation in all directions. So since we can do same calculation for pistol not only in one axis, but we can do in XYZ direction, and for each of them it will get exactly same results because due to the symmetry. Yeah, if our pistol was not like that, but it could be like that, yeah, and like in this space we'll get exactly the same thing. So there is nothing stops us. Yeah, since we can do same calculations for pistol in XYZ direction, in this case 1/2 mvx squared is equal to 1/2 mvy squared plus equal to 1/2 mvz squared, and it's equal 1/2 kc. So from here we come up with something quite big, and we'll go even bigger. We come up with something incredible, that kinetic energy of a molecule is equal to, for any molecule, is equal to 3/2 kc. This is translational kinetic energy. Translational kinetic energy. Energy of one molecule. Okay. So for one molecule, we find out what is its kinetic energy related to the temperature of the gas. Something which is microscopic, we manage to relate it to macroscopic parameter of the system. So model is accurate. The temperature of a gas is a direct measurement of the average kinetic energy of the molecule in the gas. So conclusion. So temperature of a gas is a direct measurement, measure of the average kinetic energy of the molecules. In the gas. Okay. And you can see how this K Boltzmann constant become quite a big thing. It's this K, yeah, this Boltzmann constant is a conversion factor between temperature of the system and molecule energy. Okay. Are you still with me? Following?
Yes.
Good. Okay. So since kinetic energy is equal to 1/2 mv squared, yeah, which is equal to 3/2 kc, then we can introduce the average speed. Then the average speed, which also sometimes called root mean square, RV with notation RMC, which is equal square root of average speed squared, is equal to square root of 3 kc over mass of the molecule. Okay. And I want to make it clear that this calculation model works only for ideal gases. Okay. Because why it is only for ideal gases? Because we assume that molecules fly in straight lines with few collisions. So we have a situation that molecule could go through the whole container back and forth without colliding with something else. And in this case, we calculated that its velocity change from time delta t will be equal like 2vx, yes? So we assume it's ideal gas, this collision are rare, okay? We assume molecule can fly with on in straight line with few collisions. Okay. That was how we defined. But what will surprise us even more, even if our model, how we derived it, only worked for ideal gas, this law works for liquid and gases. Our derivation was for ideal gas. This formula for ideal gas, yeah? But the law works for liquids and gases. And law is kinetic energy is equal to 3/2 kT. Okay. Okay. Now let's move forward. Are you still okay? Ready to continue? Let's try to catch up. I'll start with a new page. We'll talk about next chapter. We talk about equipartition of energy. Okay. Number 1, equipartition theorem. Guys, could I move this page or you need this page? You could move? I assume everyone, okay. If somebody need to press go slower, and in this case, I will bring it back. Equipartition of energy. So what its equipartition theorem does is equipartition theorem relates temperature of a system with its average energies. Okay. So, and the main ideas, so let me write it down. The equipartition theorem, I just want to make sure that you have the main points, relates temperature of a system with its energy, with its average energies. Okay. The main idea behind this is in the thermal equilibrium, energy is shared equally among all of its various forms. In the thermal equilibrium, energy is shared equally among all of its various forms. Okay. And each of its such form of the energy is called degree of freedom. Okay. I'm just curious, who heard the word degrees of freedom? Could you press yes if you heard this before? Let me just clear it out. And I'm just curious who heard the terminology degrees of freedom. And you can press no if you did not. Each such form of energy is called degree of freedom. At least people who are responding back and communicating, they all heard about it. Okay, good. So it's this degree of freedom usually has quadratic function. It usually has quadratic functions. So we can have, as we discussed, one kinetic energy. So yes, as a translational kinetic energy is 1/2 mvx squared, 1/2 mvy squared, 1/2 mvz squared. So this is a translational kinetic energy. Also, we can have rotational kinetic energy. So 1/2 inertia times angular velocity in x direction squares, 1/2 inertia times angular velocity in y direction. So it's rotational kinetic energy. And we could have also elastic potential energy. So if we have a molecules, we can have a situation that it's elasticity, yeah? So we can have elastic potential energy. Okay. So equipartition theorem states that at temperature T, the average energy of any quadratic degree of freedom is 1/2 kT. For system of n molecules with f degree of freedom for system of n molecules with f degree of freedom, the total thermal energy is Q thermal is equal to NF1 half KT. Okay. For any classical system, usually thermal all total energy is equal thermal energy. For any classical system, like the typical one which we see, total energy is approximately equal to thermal energy. Okay. It's becoming accurate when the quantum effects become significant, and it doesn't include energy stored in chemical bonds or the rest energy of all particles. Okay. Do you want me to write it down, or we can skip it out? Breaks or like inaccurate with when quantum effects okay, and also does not include chemical bond energy, and rest energy, which is mc squared, yeah. Guys, now I will ask you, and don't worry, I will not take it personally. I start 15 minutes later. I want to finish one small thing, which lecture will finish officially in 1 minute, and it will take me 3-4 minutes to do. Will you be okay to stay until 6:20? Please say no or yes if you're not okay. Because I officially don't want to hold the... If somebody is not okay, please let me know. Otherwise, I just want to finish one small bit so we can finish this section. I don't see no's. Okay, so I'm continuing because it's no no's in this case. Okay, so I will quickly talk about the last one. I want to talk about degrees of freedom. Just introduce them so we can finish this chapter. So thermal energy is equal to NF1 half KT. It's very big and very important formula. So let's talk about degree of freedom. Okay, so we can have degree of freedom. So we can have situation for different molecules. So we can have a different degrees of freedom. Guys, could I remove the top line? I'm removing, okay? Maybe keep it for you, something to write down. So we can have monatomic molecules. Give me examples of monoatomic molecules, guys. Monatomic molecules, guys. Helium, argon, they're monatomic. They're not paired, okay? That's they are monatomic. Okay. Okay, so monatomic, it is helium, argon, okay, and they only have translation motion. It's one molecule, and we care where it's locating. It's only translational motion. Okay, now we can have diatomic gases. Diatomic gas. An example of this: oxygen, nitrogen. Okay, and this is a most cases scenario. Most cases. This is what you will have in your homework. Yeah, diatomic gases. And for example, air. Air is combination of diatomic gases. Yes, so it has oxygen, nitrogen. It has also argon. Yeah, but it's mostly diatomic. So what it has a translational motion plus rotational. Two different axes. Okay, plus rotational. So our F here is equal to 5. And how it could rotate? So we have two molecules here. So if it's our system, and that's our molecule, yeah. So how it could spin out? Let's do it again. So we understand that we can define where this molecule locates in space, like it could be moved up and down, but it could rotate. It could rotate like that, or it could be rotate like this, yeah. So we can rotate it out, so it will be in this space or it's in this space. So there's 2 degrees of rotation. So that's why we have F5. And there is also diatomic molecules with vibration. So for example, if we keep it not at room temperature where it's quite cold, but if we heat it up, in this case, molecules will not behave like that. It's also start to have a vibration. So if we have a diatomic molecules or gases with vibration, in this case, we have a plus 2 degree of freedom from vibration. Why 2? Because it comes with kinetic energy and potential energy, vibration 1. Okay, we know when we have a vibration, it has a 2 degrees of freedoms, and this is usually happens at high temperature, not room temperature. Okay, and in this case, our F will be equal to 7, and then we have a situation of plus 2 for each mode of vibration. So for each mode of vibration, add plus 2. So for example, stretching, flexing, twisting. Okay. So for example, we have the same model. So here we have 2 atoms, yeah? And we discussed that it could be locating. We know that it could rotate like this, or it could rotate like that. And that's give us 5 models. But then we discussed that we can have a vibration. So we need to find vibrations, 2 more degrees of freedom. But for example, we can have also stretching or twisting of these molecules. So each of them give additional 2 degrees of freedom. And finally, the last one which I want to mention for you, it's a solid. And it has 6 degrees of freedoms. It is a solid. It has a free direction of vibration. Times 2, which is kinetic plus potential. So free directional vibration, and for each of degrees of vibration, we have kinetic plus potential. So if we look then at our solid, we can assume it that it's each molecule, and between them there is a spring. Okay, that's my situation of it, yeah. So each of the molecule, yes, and we understand for each, if we have more molecules will multiply, we can have a direction of vibration in each of these 3D cases, and each of them comes with 2 degrees of freedom. So in this case, F is equal 6. That's it, guys. I finished with you about the partition theorem. You'll just need to apply it. And next time we'll start talk about heat and work. Questions? Comments? As I understand, you would like me to post these notes, yeah? You prefer it. I will do it, guys, as long as you promise me, you give me pinky promise to continue to taking notes, because I understand that I'm doing it because when I did a PowerPoint, people said that they're missing writing by the hands, because when they're writing by the hands, you understand it better. That's why we're keeping the style. I will post the notes as long as you'll continue writing by your hands so you can have it in your mind. Okay? Have a wonderful day. Good luck with your homework. The last problem is easy. It's not what we covered heat and work, but I assume you know it from your previous one, or we'll cover it on Monday. Okay.
Okay.
But
Before you
everything else,
go,
no.
I wanted to ask something.
Sure, go for it.
Could you explain again for the solid why there's 6 degrees of freedom?
So does each of the molecules could it travel in solid?
What was that? Sorry.
My question for you. Let's talk one molecule in the solid, yeah? Could it travel?
No, it's bound.
It's
right?
bound, so it doesn't have a translation motion, yeah?
No.
But it could vibrate.
Right.
So
Okay.
it's in one place vibrates, and it's in 3D space, so it could vibrate in 3 direction.
Yeah.
That's why it has a free vibrational ones.
Okay.
I mean, in reality, I mean, if you go in a more complicated, theoretically, it could have a twist, but it couldn't really twist it inside of the solid, yeah? It could only vibrates out, yeah? It could not goes out of the matrix and start to vibrate, like sort of twist itself.
Okay.
Because it has a boundary. So it's only like you can look at the springs which are attached to it, and it could just slightly oscillate in one of the another direction.
Okay. Yeah.
It's a very good question. Okay.
Thank you.
You're welcome.
All right. Thanks again, Professor. Enjoy the weekend.
You too, guys. Have fun. And we will have a next, not this Friday, next Friday. I will send you email around Friday. We'll have a welcoming department meeting. So I hope to see you all. We'll talk a little bit how we will survive in COVID. Bye.
Thank you. Bye.
Bye.
Hey, everyone.
Bye, guys.
Professor.